So, good morning, everyone. I'm very happy to be here sharing some of the mottos of my group. So, I'm a professor at the Civil and Environmental Engineering Department here at UC Berkeley, and I lead the Laboratory of Science of Cementitious Materials there. And our main motivation and the main background of the work that we do is developing technologies and science-based solutions for decarbonizing cement and concrete, which are the most used construction material and also an industry that is in general considered difficult to abate. So what pushes us to work every morning, and my students and the scientists that work with me at my group, is that we need to act fast, right? So if we look at the decarbonization scenarios that we have been given by the IPCC, particularly the ones considering the 1.5 or the 2 degree scenarios for global warming, we are already at a tipping point where we need to start decarbonizing heavy emitter industries very, very rapidly. And concrete is one of these, and this is why we think that there is a new infuse of energy to concrete technology and to cement science, because this became an urgent and pressing challenge for this century. So when we look at things in perspective to all the materials that we use, and actually the stuff that humanity produces on a given year, we see that 90% of the materials that humans produce in any given time are related to construction. And this is why I think that this center is so important. And everybody here in the audience should feel so important, because we are working on a big problem, right? Like 90% of the stuff that we make ends up in construction. So it's by far the industry that consumes most of the resources. And from that 90% of material going to construction, 75% is concrete or cement-based materials, mortar renders, or materials that contain a certain amount of cement. This is a very interesting study that we published in Nature recently. And there have been also quantifications by other authors, for example, looking at replacements for concrete, right? Because we know that concrete is a carbon-intensive material. But actually, for example, if we were to replace concrete by something like timber, we would need a forest 1.5 times the size of India just to replace 25% of our cement consumption. So that puts in scale how big this industry is and how challenging it is to even think to replace it by something else. Our vision is that concrete is the material that will take us to the future with sustainable development, but to do that, we need to make it better. The other thing that I think is important to realize is where carbon in infrastructure is coming from. And there are essentially two categories: embodied carbon, which is the carbon that is put into the building in the materials and at the moment of construction, and then the operational carbon. And while these two components are important, I just want to highlight in this slide how high and how overwhelming that embodied carbon component is, especially at the beginning. And the other point that is important here is that the embodied carbon, once encapsulated in the building, there is nothing that we can do about it. And this is why we can always upgrade operating technologies, but there is nothing that I can do with the carbon that is embodied in the concrete, essentially. This is why it's so important to transition swiftly towards low-carbon concrete technologies so that we can address that embodied carbon component. The other important point here is that from a net present value of that carbon content is much more valuable to address the embodied carbon from a decarbonization strategy point of view than operational emissions that may come in many, many years. And of course, this is for buildings, but in infrastructure, this difference, this decoupling between embodied and operational is even higher. And we may think, being in the global north, so I come from Europe, now I moved to the US, that construction is a solved issue, that we don't need to do this. But the reality is that the global south is the region of our planet that is undergoing strong development now. And it's estimated that 3/4 of the infrastructure that will exist in 2050 is yet to be built. So we are going to need a lot of materials, and we are going to emit a lot of CO2 materializing this infrastructure that is only needed for these communities to achieve decent and humane quality of living. And this disparity on the projected demand of infrastructure is also reflected, of course, in the demand of cement. So you might have heard, that China is the main producer of cement in the world, but China's population is already declining, cement production is already declining, there's many, many plants that are shutting down, and we forecast that by 2050, actually, the regions that are going to be contributing the most to the cement production and therefore to the CO2 footprint associated with the concrete industry are going to be Africa, Southeast Asia, Latin America, and India instead of China. So we have a shifting polarity of where cement is being produced, and this is well correlated with the need for infrastructure in these regions. So one of the things that we work on, and one of the concepts that we have developed in my group, is something that we call the twofold strategy. So something that you might have heard is that the United States cement industry is transitioning from ordinary Portland cement, what we call type 1-2, the classical stuff that we used to get, to blended cements, type 1L, in the future, not so far away future, I guess, type 1T, ternary blend cements. So we're moving towards that. And what we do by doing so is to reduce the amount of clinker that we have per unit volume of concrete. And this is something that we have worked intensively in the past, particularly developing a technology called LC3, limestone calcined clay cements, while I was still in Switzerland. But there is another technological component that I think is really interesting for concrete producers, which is, well, we can also address the concrete mixture design. We can reduce the paste volume. We can use fillers in order to replace part of the cement paste, so to reduce even further the content of clinker, the carbon-intensive component, per unit volume of concrete. And at the end of the day, what I'm showing here in this plot is that we can achieve, and we have shown this with sound evidence, concrete with comparable properties with about a quarter of the CO2 footprint that what we are producing today. So concrete today, and I want to be very clear with this message, is an environmentally friendly material today, but we use so much of it that the carbon footprint is very, very important. And there is a lot of room and technological space for doing things better in the future. And we have a long pathway ahead. So if we compare, for example, the reality of the United States, which is the orange fringe here in the upper band. So these are the numbers that the NRMCA reports every year, the National Ready Mix Concrete Association. And this is the average CO2 footprint for different concrete strengths. We can compare that with the UK, which is the numbers in yellow just below what Chile is doing, which is a country that is famous internationally for using a very low clinker factor for many, many decades, and what we have been accomplishing with LC3 in green at the bottom. So essentially what this plot is illustrating is that for any given strength that you want, we can make that concrete with about a third to a quarter of the CO2 of what you can find in the market today. And on these decarbonization strategies, and to close my pitch talk this morning, I want to illustrate that this is interesting and appealing for industry because it's also the opportunities that we have that likely will cost us the same or even have the potential to reduce production costs. So if we look, for example, the marginal costs of clinker production is about $30 to $50. This is not market price, please. This is what it costs to our cement producers to actually make clinker. And reducing cement content, reducing paste content, optimizing the concrete mixture design is essentially things that we can do in everyday civil engineering practice and are likely going to be very low cost or enable us to even lower the cost of concrete compared to what we have now. And I think that there is this interesting dichotomy between this and comparing with the alternative, which is like we will just take the CO2 and carbon capture and store it. The best estimations that we have is that if we go down that pathway, it's going to increase the price of cement 2 to 4-fold the prices that we have now. And in an industry with small margins where money is made out of bulk, it's going to be very difficult to justify this. And I think that the industry is already reacting to this reality by reducing the projects that we see of CCUS once public funding became unavailable for these kind of things. And this is both in Europe and the USA. It's not necessarily tied only to political scenarios, but to the realization that it's very, very difficult and it's going to be very complicated to make money in a scenario like this. So my message is that we should be doing everything else first before we even say the word carbon capture and storage. So in this Nature paper, and this is my last slide, we illustrated different approaches that we can use to try to offset the increased amount of greenhouse gas emissions associated with this booming of development in the global south. Things like timber substitutions are not going to take us very far, and the main reason for that is the limited stock of the material that we have. But everything that I have discussed in this presentation, particularly better design, better concrete, and better SCMs to make blended cements, are likely to reduce cost and will take us most of the way down there, so that if we want to be carbon neutral, what we have to, in the end, carbon capture and storage is going to be a much smaller amount of that CO2. So the message is less clinker in cement, less cement in concrete, and less concrete in the building. So to conclude, my takeaway message, there is no magic solution. What I want to say with this, there is no replacement for concrete, realistic replacement for concrete. We're constrained by the composition of the planet on this. We have to reduce the clinker content, so that means continue moving towards highly substituted cements, and we need to help, the cement producers facilitating adoption of these new and emerging cements in industry, and we are happy as academia to support industry in adopting these new formulations of cement that are going to become available in the country in the next 5 to 10 years. We have to minimize cement content, so this is something that we need to work with the concrete producers, and we need to optimize structural design, of course without compromising safety, which is a value that is above decarbonization in all cases. All the above likely lowering the cost. And before moving to Q&A, I just want to briefly introduce my research group. So my laboratory is called the Science of Cementitious Materials Laboratory. So I'm actually trained in material science, not in civil engineering, although I'm a faculty at the civil engineering department here. So what we do is essentially developing fundamental scientific formulations and solutions and transition and translating those for industrial applications. The most notorious of that is of course, limestone calcined clay cements, which today is produced in every continent. So with this, I would like to conclude and invite for any questions if we have. Thank you.